All right. I think we can get started. And I will first introduce you before we start. Hello, everyone. Welcome back to Ethics Seminar Series. I'm John, the seminar coordinator, and together with me is Miss Cassandra Medley, Kathy. Kathy is our communication specialist, and Kathy and I will be the moderator for today's seminar. And today we have our honorable speaker, Professor Annie Zipperman, joining us from Harvard University. Let me give you a few tips before we start up. So this seminar is being recorded and will be later published on our YouTube channel. Please feel free to ask questions in the chat, and Kathy will read them out loud. Or you can raise up your virtual hand by click the raise hand button, and Kathy will unmute you and appropriate. And today's agenda is that we will first introduce the speaker and let him do his presentation, and then we will come to the question session. But please feel free to ask any questions even in the middle of his presentation. And okay, so now let me give a brief introduction about the speaker right before he starts. So Professor Annie Zipperman is a professor of oceanography and applied physics in the Department of Earth and Planetary Science and in the School of Engineering and Applied Science at Harvard University since 2003. He teaches oceanography, climate, and applied math. Prior to then, he was a postdoc and then a faculty member at the Weizmann Institute of Science, Israel. His PhD in physical oceanography is from the joint program in oceanography of MIT and the Woods Hole Oceanography Institute. His research interests include large-scale climate and ocean dynamics, El Nino, thermohaline circulation, past and future climate dynamics, including abrupt climate change, warm climates, glacial cycles, snowball Earth, as well as advanced methods of data analysis. So let's welcome the speaker, and now I will give the ball to Professor Annie. Professor, please proceed.
Great, thank you. Let's see, I'd really like people to be able to ask questions during the talk. So I'm wondering whether someone could now raise their hand so that Casey can see you, and maybe you could ask some question. Ask me what the time is for me right now. So Casey, no one raised their hand?
Mike is. You're muted, Mike.
I did. Hi. Yeah, I just wanted the source of the cloud photo and its significance.
Okay, say again.
Simply the source of the title slide photo and its significance for the topic.
The background.
Yeah.
Directly from the internet. Great, thank you. So now we know that this works. I'm really hoping that if you have a question, and I'll stop from time to time, that you would signal to Casey by raising hand, using the raising hand feature. I think you click participants and then raise hand, and then I'd love to hear from you. So let's see, I'd like to talk about two different subjects. The first one would be suppression of Arctic air formation. So that is how the formation of very cold air, for example, above Canada, that then penetrates into the present-day United States, how that could be suppressed in a warm climate. And the second part would be about a link between sudden stratospheric warming events and the Madden-Julian Oscillation in a warm climate. And I'm going to introduce everything, so if you haven't heard about this, then I'll try to introduce them. So let's start with the first subject. This is the Arctic air suppression. Here's an example of an Arctic air event. So this is from a website of a TV station in Minnesota, January 2014. and they show you this very cold air coming from Canada, and they tell you that the temperature would be -40 to -65 with wind chill, and that it takes your skin, exposed skin, to freeze 5 minutes outside, so very unpleasant. So that's what happens today in Minnesota and Wyoming, I suppose, and so on, very frequently in the winter, right? On the other hand, here's what happened there about 50 million years ago. Same place, so you see these dark spots here on the map are places where people found fossils of crocodiles, alligators, palm trees, and so on, in the same place that today have these very cold events. And because these trees and animals are not frost intolerant, that is, not survive sub-freezing temperatures, this means that the temperature never went below freezing for millions of years in these areas 50 million years ago. And we're trying to understand what is the reason for the lack of Arctic air events at that time. And as I'll show you later, this issue also has relevance to future warm climate as well and to present observations of global warming. So let's do a first experiment. I'd like to stop and see if anyone has questions about my motivation. Kezi?
I see no hands raised right now, so I think everyone is good. I'm looking.
Good, good. Okay, let's just go on. Unless there's something anyway. Great, so hopefully you understand. It's very cold in these places in the continental United States in the winter right now, but in the past these places never experienced any cold events, and the question is why. So let's try to see how these cold events progress at present. So for that purpose, we followed a paper by Judith Carey, 1983. We just repeated her experiments, essentially. We took a single column model, the Worf model, and it's a single column. So here's the initial conditions. You have temperature on the x-axis, pressure on the y-axis, and each line is a different day. So this is day 0. We assume that the air column starts over the ocean. It's 0 at the bottom, and then there's some lapse rate. Then after 2 days only, you see that the temperature at the bottom, so now we assume that this air column that started, say, over the Pacific Ocean moved over Canada, and now it starts cooling. And within 2 days only, the surface temperature over Canada of this air column that just came from the ocean is -15, and after a few more days, it gets to -40. So there's very, very rapid cooling, and that is this Arctic air that is formed over Canada and then moves over the present-day United States. Okay? So you can see here that the surface temperature cools by about 60 degrees Celsius in 2 weeks, and a strong inversion is developing. Look at this strong inversion here. So it's getting warm as you go up, and then the normal lapse rate. Okay. Yeah, so please feel free to signal to Kezi anytime you want to ask a question. I'm happy to stop as soon as she lets me know that there was. Okay, so that's what happens today. Let's see what happens when we now assume that this is a warm climate and the ocean is much warmer. So now we're assuming that the air starts over the ocean, but the ocean is 20 degrees warm. We'll go into more intermediate cases, but let's go to an extreme case just to see if something interesting happens. So the air again starts over the Pacific Ocean, high latitude. Now we're assuming the high latitude Pacific is 20 degrees C in the winter. Clearly not realistic today, definitely in the past, maybe in the future. So what happens here? Well, this is day 0, just like before. The only difference is that we now start at 20 degrees C. After 2 days, there still is a significant cooling of about 10 degrees instead of 15. But then look what happens after that. Day 4, there's hardly any cooling. Day 6, there's hardly any cooling. Now there's a little bit of cooling. If you compare this to what we saw before, where there was a very large cooling, within day 4, we were at -25. Here we're only at about 12 degree cooling, and we're still far above 0. So when we start with a warm ocean, Of course, the temperatures are warmer, but also the cooling is much, much smaller. And the question is, what prevents the air that moved from the ocean to over Canada during wintertime with no solar radiation, essentially, not to cool at this point? Okay. So again, this is summarized here. Day 1 cooling is similar to what happened before, except it's 10-degree cooling instead of 15. But further surface cooling is suppressed. So let's see what is the reason for the suppression when we start with air over a warm ocean. So here's the answer. Let's look only at the orange curves in this case. So what's shown here is the temperature as a function of time. So this is day 0 to day 14. The x-axis is time. And you can see the surface temperature. You can see here a very small cooling initially. And then there's a long plateau in which temperature hardly changes, and then it starts decreasing again. And this long plateau above 0, 0 is the dotted line right here. This long plateau above 0 is the reason the air stays above freezing for a long time. And if you think about it, if the air stays above freezing for a week, or maybe even 10 days, that air column is then moving off North America and being replaced by a new air mass from the ocean. So effectively, we've explained why air does not go, why the temperature doesn't go below freezing during winter time if the ocean is warm, right? The assumption here is that the ocean is warm. So let's see, what is the reason for this sustained plateau? So if you look at the next one here, this is net long wave cooling. And you can see that there was large cooling in the first few hours, but then this orange curve very close to 0 means that there's very little long wave cooling. And the reason for that is this. This is a cloud liquid, so you have very large signal of cloud liquid developing. And if you look at this picture again, you see these green patches. Green patches mean water clouds that have developed, and you can see that after 2 days, in fact, if you look at this after just a few hours, water clouds developed at the surface, and these water clouds have a very strong greenhouse effect, and that greenhouse effect prevents further warming. And only when these clouds finally dissipate do we get cooling to renew, and then the air freezes. But of course, as we said before, by that time, the air column might be off the continent into the Atlantic Ocean, being replaced by new moist air from the ocean that can again cool, condense, lead to clouds, and the clouds prevent further cooling. So the mechanism of Arctic air suppression here is that the air starts moist over the ocean. As soon as it gets over the continent, high latitude continent, say Canada of present day, it cools. The slightest cooling causes these clouds to form, and the clouds have a very strong greenhouse effect that prevent further cooling from happening. So these low clouds that form in a warm climate when we start over a warm ocean prevent the Arctic air events from occurring.
We actually have a question from Mike
Wonderful.
Evans, who's
Really
unmuted
glad.
now.
Let's hear.
Mike, are you there?
No, that was just a comment. I was just making a note in the chat. Please go on.
Please tell me what the comment was.
I was just thinking that the surface temperature gradient was going to be large as it went to the continent, but you already explained through how that affects the results. So thank you.
Right. So this is a column model. So at the moment, we can't address a question like that, right? When we're assuming that the ocean is warm and the continent is much colder, this leads to a surface gradient. You wonder whether that would change the airflow or change the wind regime or anything like that that would invalidate what we're talking about right now. So I will shortly show a 3-dimensional model result that supports this, that does include the effect of this gradient that you mentioned. Great question. Any other questions?
None that I can see at this time.
And was there another one? Or?
No, I don't see any.
Okay, let's continue. Great. Okay, now look at this picture right here. This shows something very surprising. So here we're asking, how long does it take for the temperature to drop below 0 degrees C as function of the initial temperature over the ocean, right? So we assumed before that the temperature was at freezing, and then we assumed that the temperature was at 20 degrees Celsius at the surface over the ocean. Now we're doing this experiment and again at much higher resolution in terms of the initial temperature, and we're checking how long does it take for the air to drop below 0 degrees C. So of course, if the temperature is already below 0, then it doesn't take any time. But even if it's as cold as 10 degrees, the time it takes to get to freezing is less than a day. However, if the initial temperature, the surface temperature of the ocean, is more than 10 degrees, the time to get to freezing, the time that it takes the air to cool to freezing, increases now very non-linearly. So I'd like to explain this break in the profile. So let me explain again what this break is. What we're plotting here is as function of the temperature of the ocean, which is also the initial temperature of the air column, right? We're starting over the ocean, and then we're pretending that the surface becomes, say, snow over Canada, no sunlight, and it starts cooling, right? And we do this many times, many different runs, for different initial temperatures that correspond to this ocean surface temperature. And what's plotted on the y-axis is how long does it take the surface temperature to go below freezing. And what we see is that it takes very little until the temperature of the ocean is 10 degrees, and then it increases very rapidly. So it takes much, much longer to get to freezing at that point. So let's see why that is. Why is this nonlinear behavior of the time to freezing? So for that, let's look at these two schematic plots here. So start with the cold initial conditions. This is time and temperature. So if we have cold initial conditions, the initial cooling, if we're less than 10 degrees, the initial cooling takes you immediately under 0, and therefore it takes very little time to get below freezing if your initial temperature is less than 10 degrees. And then once you're below, once this initial cooling happened, we do get some cloud formation, but at that point the temperature is already below freezing, so we get this suppression of long wave cooling, but this plateau happens below 0, and therefore this doesn't affect the time to freezing, which is the essential thing we're interested in given these past climates in which we know that temperature never went below freezing. However, if we start with warm initial conditions, we still get this rapid cooling at the beginning. We move the air column from the ocean to the land. It starts cooling radiatively immediately because there's no shortwave and the surface is very low heat capacity. But the cooling doesn't bring us below 0, and now we have clouds, and these clouds prevent further cooling and keep us above freezing for a long time. And only when the clouds dissipate, we get continuous. We get the cooling to continue. So the reason for this break in the profile is that initially, for cold initial conditions, the initial cooling gets us below 0, while for warm enough initial conditions, the initial cooling lifts us above 0. The clouds prevent further cooling until the clouds dissipate. And this period here can take a week or so. I'm pausing just in case there's any question about this. Okay, feel free to ask. I'll stop if you try while I'm continuing. So this is the plateau of suspended cooling due to the low clouds that we mentioned before. Great, so now we move to three-dimensional GCM simulations of this to address questions like the one that was asked before, and we did the following experiments. We prescribed surface temperature, so this is pre-industrial surface temperature in a three-dimensional atmospheric model. This is the community atmospheric model, and then we prescribed surface temperature that is RCP 8.5 at 2090 and RCP extended at 2290, and then this is the most extreme case in which we take the extended RCP 8.5 at 2300, plus we set the temperature to 20 degrees anywhere that it's not colder than 20 degrees. So we have anything from present day to very warm initial conditions. And for all of these, we run the three-dimensional GCM and look at winter temperatures, and here's what we find. So this is the 1% coldest daily temperatures in pre-industrial run, or you can think about this as present day or before. And you can see that the coldest temperatures are like minus 45 degrees Celsius over North America. no surprise. However, when we use warm oceans, and the land still adjusts prognostically, right? Then you see that over the oceans, the coldest temperature that you get is more like -5. And this is the coldest 1% of events. So even the very coldest events are much, much warmer than before. You could look at the PDF of temperature. The blue is the pre-industrial, and you can see the PDF centered around -40 Celsius, while this run with very warm initial conditions, the PDF is centered around maybe 10 degrees Celsius. So the question is now, does this GCM run have anything to do with the results of the column model I showed before? And the answer is obtained by looking at low clouds, and you can see that this is change in low clouds, and you can see lots of low clouds developing over northern North America, explaining this warming of the coldest events. So again, the GCM is consistent with the column model, because when you increase the sea surface temperature, when you increase the temperature of the ocean, you get lots of low clouds during winter over northern North America, and this prevents these very cold winter events from happening. Okay, great, continuing. We look at the vertical profiles of temperature at 65 north and 100 west, and you see that this is the present day or pre-industrial run, and you can see this very strong inversion during winter. And if you look at the warm ocean temperature case, then you can see that the inversion completely disappears, just like what happened in the column model. So the results of the GCM are completely consistent with the results of the column model. You get low clouds, the inversion is suppressed, and the surface temperature remains warm because of the long wave trapping of the low clouds. Okay, let's see. So looking at the time, and maybe I'll skip this and this. Let me just say that this is relevant to present day observations and future climates as well. There isn't being a polar amplification, so this is warming in a 4 times CO2 model experiment in CMIP5. I think this is RCP 8.5 essentially. So you see the warming is function of latitude, and you see that the most latitudes warm by say 4 degrees, but the Arctic warms by 20 degrees. And this paper, which you may know, analyzed the reason, and they found that the most important reason is albedo, but the second most important reason is lapse rate. And I'll explain what they mean by lapse rate in 1 second. And I'm going to claim that our mechanism with the low clouds developing explains this lapse rate feedback. So here's the tropical lapse rate. When the temperature warms in the tropics, it warms by some amount at the surface, and because of the response of the moist adiabatic lapse rate, the warming is higher at high altitudes, and this means that there's a negative feedback on the surface warming. I don't want to get too much into this. However, in the Arctic, the following thing happens, and already in observations today, and definitely in model simulations of future climate. This is the pre-industrial temperature profile with the inversion. And what you see in these models is that the inversion is cancelled, eliminated, and you get just a lapse rate. So in this case, the surface warming is much larger than the high altitude warming. And this is a positive feedback on the warming. Again, I'm not getting into why, I'm happy to answer that later. And this lapse rate behavior explains why the Arctic warms much more than the tropics, because the lapse rate feedback is negative in the tropics and positive in the Arctic. So now this elimination of the inversion is explained, of course, by our mechanism. If you look at this paper that analyzed this, they try to explain this Arctic lapse rate behavior, but they don't mention low clouds. But clearly, our mechanism is able to explain why the Arctic lapse rate behaves the way it does. Okay, I'm going to skip this and go to the conclusions of this part 1. So I told you about Arctic air formation, which is the rapid cooling of marine air when the air moves from the ocean to land. And this was analyzed by a few papers. Kerry in 1983 is one. We find that in a warm climate, there's delay freezing of the cloud water, and there's much more moisture in the air that's coming from a warm ocean just because of the clouds clapeyron. And this leads to a prolonged period of low clouds and therefore delayed surface cooling and can keep the surface warm. And this explains possibly, or helps explaining the survival of frost-intolerant palm trees and crocodiles during, say, 50 million years ago. And it also explains observations and predictions of enhanced warming due to the lapse rate feedback in the Arctic. And we show that this is a highly nonlinear effect. And I'd like to stop here and see if there are any questions about part 1 before I move to part 2.
Ross, you're unmuted.
Okay, great. Thanks. It's very interesting so far. My question relates to, have you actually compared this quantitatively to reconstructions of ocean temperature during these so-called equable climates? Quantitatively, does this hold with what SST used to be?
Great question. So, yeah, so as we saw, our estimate is that the temperature of the ocean needs to warm by at least 10 degrees for this mechanism to work. And I think there's no question that the ocean during these warm periods was at least 10 degrees warmer than today. For example, there's evidence that the deep ocean, instead of being around 0 today, was maybe 12 or 14 degrees Celsius. And the deep ocean water comes from the high latitude. So this means that the high latitude ocean was no colder than 12 or 14 degrees Celsius. So it seems to be consistent with this claim. Thanks for the wonderful question. Anything else? It's difficult without seeing your faces, but I guess we'll do what we can, right? Okay.
Looks like we have one more.
Great, great.
You are now unmuted.
Oh, okay, thank you. You just showed the plot earlier, so the lapse rate. You see the increased CO2 will lead to a reduced lapse rate in tropics and an increase or more steep lapse rate in the Arctic. In general, if with the increased CO2, there will be the greenhouse effect, the surface temperature will rise. And then the whole Earth as a for radiative balance, the upper either troposphere or stratosphere, somewhere upper level, the temperature must be cool. So the total radiation will be balanced with the income. And that there is actually some evidence to say that in the past, how many years from the microwave sensor, the surface or lower level temperature is increasing, the upper level is decreasing. And that will imply a steeper lapse rate. But of course, that must be a global average. Are you saying that somehow these two are offset, so the overall the lapse rate still become steeper, like in Arctic, or something I missed?
Great. And if I understand the question, you're saying in the stratosphere is going to cool, and that will obviously is not included here. But of course, the emission level is within the troposphere. So even if the stratosphere cool in a warmer climate because of the increase in CO2 as we expect, what's important is the lapse rate within the troposphere, and that lapse rate is different. The response to that lapse rate is different in the tropics and in the Arctic, the way it's drawn here. In the tropics, the lapse rate becomes less strong, and in the Arctic, it becomes stronger because of the elimination of the inversion. So it's true that the stratosphere is cooling in a global warming increased greenhouse scenario, but that doesn't come into these feedbacks because the emission level, the highest emission level, the level of last emission as sometimes it's referred to, is within the troposphere. Great.
I see.
Thank
So
you.
your Z here is essentially the tropopause.
That's right. Exactly.
Okay.
Wonderful question. Thank you.
Thank you.
Okay, with that, I'd like to move to the second half. So this is the work of my student who just graduated, Waning Kang. She's now a postdoc at MIT. Before it was the work of postdoc Tim Cronin, as you saw his name there, who's now an assistant professor at MIT. Let's see. So this is about southern stratospheric warming events and the Madden-Julian Oscillation. So let me first introduce what the southern stratospheric warming events are, and I apologize, I'm sure most of you know this. Here's an example of a southern stratospheric warming event. I'm hoping you see the animation okay. You see the stratospheric polar vortex going around. This is the reanalysis NASA December 2012. You see the polar vortex going around thousands of kilometers big. And now it's beginning to become smaller and smaller, and it breaks into 2, and now it breaks into 3, and now it's just a mess, and it's completely gone, basically, right? So this happens 6 times per decade over the satellite period, and whenever this happens, there are extreme weather events in mid-latitudes, very cold temperatures in Chicago or in Europe. Some time ago when this happened, Europe was colder than the North Pole and so on and so forth. So a very dramatic event that lasts just a few weeks. Okay, so these are southern stratospheric warming events in the stratosphere, obviously. Okay, here's another view at southern stratospheric warming events. So what you see here is in red is the stratospheric temperature, and you can see the seasonal cycle, very strong seasonal cycle in the stratosphere at 10 millibar. So you see warm summers, cold winters, but sometimes, like this event, during winter, you get very strong warming of maybe 40 degrees Celsius within just a few weeks, a couple of weeks, 2 or 3 weeks. And when this event happens, the jet, the polar night jet, the polar vortex, if you want, it decreases. So this is the blue line. You see the polar night jet decreases and the zonal mean goes below 0. That's what we saw in the animation before. And this is what the normal polar vortex looks like. This is an event, southern stratospheric warming event, in which this polar vortex was just displaced, and this is one in which it was split. So the displacement events, the split events, there are events in which the polar vortex is just completely shattered. And some GCMs predicted there would be more events in southern stratospheric warming events in the future. Some predict less. We basically don't know whether this would be more or less frequent in the future. And let me just say one thing about this. The reason we're interested in southern stratospheric warming events is that they lead to extreme weather in mid-latitude, so I won't go into the details here. But if we are able to predict southern stratospheric warming events, we're able to predict extreme winter weather events in the high latitudes. And if the statistics of southern stratospheric warming events change, then the statistics of cold events in winter change as well. So we want to know about this, obviously. So that's the first hero of this part, is southern stratospheric warming events. Moving to the next part, so the other protagonist here is the Madden-Julian Oscillation. So you must have seen this animation. What we see here is a precipitation anomaly in the Indian and Pacific Ocean that is involved in the Madden-Julian Oscillation. So you see a positive anomaly, and clouds develop over the Indian, propagate toward the West Pacific, Central Pacific, and then disappear, and then another one comes from the Indian Ocean, and then again and again. The time scale is roughly 40 days, 20 to 100 days. The velocity of propagation is 5 meters per second, and this is wave numbers 1 to 2. So this is the Madden-Julian Oscillation. So we have southern stratospheric warming events and the Madden-Julian Oscillation. So I'm going to try and connect them now and then see what the connection between them is going to do, possibly in a warm future climate. That's the thing. All right, so This is from one of our papers in 2014, but many other people came up with the same finding, that we expect the Madden-Julian oscillation to get much stronger in a warm climate. Let's just choose one of these, say this one. This is a Wheeler-Pilates plot, so frequency wave number plot. This is 1 times CO2, and G is 1 times CO2, and panel H is 4 times CO2, and you can see stronger reds here in this plot, and this stronger reds means that there's a stronger Madden-Julian oscillation. This is also seen in the Hofmöller plots and so on, but basically the point is that we think the Madden-Julian oscillation will get stronger in a warm climate, and there's a mechanism for that this paper explored. And so there's a good reason to think that the Madden-Julian oscillation will get stronger in the future. Okay. Going back to present day, forget about strengthening in the future. There's this nice paper by Garfinkel et al. 2012 that shows what these colors basically show, never mind the details, is that there's a correlation between the polar cap temperatures, so the stratosphere 10 millibar, and the MJO phase. So this means that even today, there's some signal of the MJO that arrives to the Arctic stratosphere. It's not strong and it doesn't affect southern stratospheric warming events, but it affects the climatology of the stratosphere. So given that the MJO is going to get stronger, as we saw in these plots, and there's already a connection in present day, this raises the following question, which is my question for this one half of the talk. Would the stronger tropical Madden-Julian oscillation that we expect in a future warm climate change the southern stratospheric warming events? So again, we know that the MJO weakly affects the stratosphere today. We know that the MJO will get stronger in the future. We think it will get stronger in the future. The question is, will it affect southern stratospheric warming events in the future? Let me stop for just a second to see if there are any questions about my question. Questions about the question. Okay, I'm assuming we're good. So
I see no questions so far.
Great. Is there a question right now?
No, all questions.
Okay, great, thank you.
Right now.
Excellent. Okay, well, let me tell you what the answer is to that question. So again, the question is, will the southern stratospheric warmings, will they change because the Madden-Julian is stronger? So here's what we did here. We took a simple model and imposed a stronger Madden-Julian oscillation, and we're plotting the strength of the polar night jet, the strength of the polar vortex. Blue means weak MJO forcing, and red means strong MJO forcing. And it turns out that as a result of the stronger MJO forcing, the number of southern stratospheric warming events double. Okay, so we have a stronger MJO that leads to twice the number of southern stratospheric warmings. What is the mechanism? Before I get into details, I want to give you a preview of the mechanism. So here's the idea. This is the equator, and this is the North Pole right here. This axis is the vertical axis. So the surface of the atmosphere is right here. This is the troposphere and the stratosphere. So we have the MJO happening at the equator in the troposphere. And we have the polar night jet, where the southern stratospheric warming events happen, is at high latitudes in the stratosphere. So the MJO gets stronger and emits waves. These waves interact with the tropospheric jet. The tropospheric jet changes. This leads to more stationary waves. These more and stronger stationary waves affect the polar night jet, and this leads to more frequent southern stratospheric warming events. So this is a one-sentence summary of the mechanism that I'm going to tell you about now. Let me just repeat it just in case that wasn't clear. So in a warmer climate, we believe the MJO might get stronger. As a result of that, it emits stronger planetary waves, so Rossby waves are emitted by the MJO. These Rossby waves interact with the mid-latitude tropical jet at 30 degrees north in the troposphere. The jet changes in a way that I'll show you and emits more stationary waves. The stationary waves propagate up to the stratosphere and leads to more collapses of the polar night jet and more southern stratospheric warming events. Okay, that's the short version. Let me show you what tools we are going to use. So we're going to use an idealized dry dynamical core model, the Helzward style, and we're also going to use a much more realistic one, the Wacom specified chemistry model. So in the first one, we just imposed the MJO as heating, and in the second one, we messed with the entrainment rate in the convection parameterization, and this leads to a stronger MJO signal. And we look at both the idealized and the realistic GCM and see what the mechanism is of any possible effects of the MJO on the southern stratospheric warming events. So start with the result I already told you about. You take this idealized model and you force it with a stronger MJO that is imposed. And you plot the forced minus unforced climatology, and you see that the climatology warms. So this is the temperature. There's warming in the Arctic. This is the stratosphere. This is the surface here. This is the North Pole. So there's strong warming, climatological warming. At the same time, if you look at the polar night jet, you see that the number of events per period of integration of the model increased from 30 to 59. So essentially a doubling of the number of southern stratospheric warming events because of the strengthening of the MJO. So this is a totally idealized GCM, no convection, no moisture, and so on. Let's see what the more realistic model does. So here's this Wacom, and same thing exactly. You change the entrainment rate in order to make the MJO stronger, and you double the number of southern stratospheric warming events from 10 to 21. So we have a clear result that as you change the MJO, the number of southern stratospheric warming events increases, in this case, even doubles. Now the question is why? Again, please feel free to interrupt me by raising your hand at any time there. So it turns out that the reason for this is... Yes, please.
You're unmuted, Taksu.
Thanks. My question is, when you're talking about the SSW, is there a definition of how much temperature is increased? You define that is the event. You talk about just now, you mentioned about 5 degrees. It may be a little bit smaller.
Great. Yeah, wonderful question. Yes, we define, there are major SSWs and minor SSWs. We're looking at major southern stratospheric warming events. And the typical definition is that the zonally averaged U velocity, zonal velocity, becomes negative instead of being positive. You see these zero crossings here. You can see a seasonal cycle here, but if you look at this area right here, I hope you can see right here.
Yeah.
The red line goes below zero. This is a southern stratospheric warming events in the run with stronger MJO forcing. And here you have the blue line crosses the line. So this is a southern stratospheric warming event in the run without an increase in the MJO amplitude. So this is the criterion we're using. That's the typical one people use of not the temperature, but in fact the velocity, the zonally average polar night jet velocity. When that
the velocity,
I'm sorry.
Yeah, reversed, right? Yeah, the zonal mean U components is reversed. Yeah.
Exactly. Yes, exactly. When that happens, the temperature warms by tens of degrees. In addition to that, what you see here is not the southern stratospheric warming, but this shows that the climatology is also changing. The climatology is only changing by 5 degrees, but the warming during each of these events is possibly 40 degrees Celsius.
Okay, thanks.
Thank you for the question. Wonderful.
We have another question from Paul Newman.
Yes.
And you are unmuted, Paul.
Oh, can you hear me?
Yes.
Yes.
Yeah, I was just going to ask about the plots on the left. Is the stippling statistically significant then?
Yeah, exactly. Yeah. I mean, this is the idealized model. We can run it forever and get it to be statistically significant anywhere because, it's cheap to run. But you could see that the more realistic model that was more expensive to run and is still statistically significant in the areas of interest. So you can see a change in the climatology of the zonal velocity, zonal mean velocity, and you can see the small warming of 5 degrees. I mean, it's not small, but it's small relative to the warming during these events.
Okay, thanks.
Thank you. Okay. So let's see, looking at the time, we're still okay. Okay, so the reason for these sudden stratospheric warming events is waves propagating, upward propagating Rossby waves. We know this since the work in the 70s that explained sudden stratospheric warmings, but for the first time. So the question is what waves? And this analysis looks at waves at the period of the MJO, so 40-day waves. It also looks at stationary waves, and it looks at other waves that are not stationary and not 40 days. And what we find here is that the main reason for the strengthening of the number of sudden stratospheric warming events is the stationary waves change. I'm skipping, these are EP fluxes, and so I'm not showing you the details. I'm telling you the bottom line is that stationary waves get stronger, and this leads to more SSWs, more sudden stratospheric warming events. And the question is, why is it that the stationary waves change when the MJO gets stronger? So this is the explanation right here. We did the following experiment. We take again the idealized model and we force it with an MJO at different sectors. So I don't know if you can see this. This is North America and this is Asia. So we're looking at the Pacific here. The contours are the U velocity, the zonal velocity in the atmosphere, in the troposphere. And we're forcing here with the MJO that is extending from the Indian to the middle of the Pacific. And this is when there's no MJO forcing, the jet looks like this. It's pretty uniform. When we do include the MJO forcing, the jet gets stronger here and weaker here. So it becomes very zonally asymmetric in the Pacific. If we move the MJO forcing to a different sector, say the one in the East Pacific, then the jet becomes even more uniform. So what's happening here is we include the MJO forcing in the Indian Ocean and the Pacific, and this makes the jet very zonally asymmetric. Now, zonally asymmetric jet, by definition, means more stationary waves. Stationary waves are deviations from zonal symmetry. So this result by itself shows you that the waves forced by the MJO lead to a stronger jet in this area and weaker jet in this area. And this zonal asymmetry is causing more stationary waves, and these stationary waves force more sudden stratospheric warming events to happen. So that is the mechanism. The MJO gets stronger, the mid-latitude jet becomes less zonally symmetric. This means more stationary waves, and the stationary waves propagate to the stratosphere because they have the right wave number of k equal 1 and 2 and lead to more sudden stratospheric warming events. And we verified this by complicated experiment. I won't get to this. Let me jump to the conclusion so that we have a few minutes for questions in case there are any. So what I was trying to tell you is that we expect stronger Madden-Julian oscillation in a warmer climate. And we find here that a stronger Madden-Julian oscillation leads to more frequent sudden stratospheric warming events. And you see here the more frequent event. The red line is the model forced by stronger MJO, and there's twice as many events, and the climatology changes as well, but that's interesting. Okay, the mechanism, as I said, is that as you increase the MJO, this emits more Rossby waves. The Rossby waves lead to a more zonally asymmetric mid-latitude jet, and this deviation from zonal asymmetry of the tropospheric mid-latitude jet means more stationary waves, and these stationary waves propagate to the Arctic stratosphere and leads to more sudden stratospheric warming events. And there's been a recent work by Maloney et al. In which they show that in a warm climate, the MJO precipitation may strengthen, but in fact, the winds may not strengthen, but in fact weaken due to changes in the static stability in the warm. We're looking into this right now by running, let me tell you about the next issue first, and then I'll go back to 4. So in order to study this thing in a more realistic way, we need a model that simulates the MJO and also simulates southern stratospheric warming events. There's no such model at present because in order to simulate the MJO, currently you need a super parameterized model, one of these models that are about 100 to 200 times more expensive to run than a normal GCM and has a cloud resolving model in each grid point, in each grid cell. But these models don't have a stratosphere yet. So we're working with Dave Rundle, and Waning, my student, and Dave and Mark and I have been meeting regularly, and under the leadership of Dave Rundle, we've been developing this super parameterized model, super parameterized community Earth system model that has a stratosphere. And so we're still working on this. There are many difficulties. And so far, we do see that as we impose an RCP 8.5 in that model, the MJO gets stronger in a way that not only the precipitation and heat and rate change in a future climate, but also the dynamical response gets stronger. So I'm optimistic that number 4 is not an issue. And I'm hoping that eventually this effort would lead to a model that simulates both MJO events and southern stratospheric warming events, and will finally be able to test this hypothesis that southern stratospheric warming events might become more frequent in a future warm climate. And that's the end of this part, and I'm happy to take more questions at this point.
We have a question from Paul Newman, who's unmuted.
Yeah, I was just wondering about the how consistent are these results with Chaim Garfinkel's paper?
So he was looking at an reanalysis and connections in reanalysis between the MJO and the stratosphere. That paper and several follow-up papers that they've recently motivated this work because our thinking was that if there is a present-day connection between the MJO and the stratosphere, even if it doesn't affect southern stratospheric warmings, maybe if the MJO gets stronger, the connection between the MJO and the stratosphere would get even stronger, and we'll have more frequent or less frequent or something events. It turns out we get more frequent events. So I would say that this work is partially motivated by these Garfinkel papers.
Okay. Well, I was just wondering because you can do the same statistical analysis that Chaim did, and so that would give say the phasing that he showed as a function of the phase of the MJO. So I was just wondering if you'd made a similar plot for the idealized models.
We did. It looks exactly the same, except more regular. Yeah.
Great. The other question I had was, so if I'm looking at this, I'm thinking the MJO is impulsively forcing a Rossby wave that is then propagating northward. That appeared to be in your EP flux diagnostics. You kind of see that, and so as it propagates northward and then upward into the stratosphere, that seemed to be the result. But am I right? Am I interpreting that right?
Yes, in fact you are. Let me see. Here's more of that. So here's more information about this propagation. What you see here is in a zonally average picture. You see this is the equator and the high latitude. You see this propagation here. This is MJO phase, and you see the signal from the equator propagates poleward. And if in the latitude longitude plot, you also see signals of PV propagating from the equator to the to the Arctic and so on. So we followed that signal of these waves both in the zonally average picture, in EP fluxes, in group velocity, and in potential vorticity analysis. You can see here the lower stratosphere, 60 to 80 millibar. And we seem to be finding these anomalies that propagate from the MJO to the polar stratospheric vortex.
So one final question before we go, Eli, or before I have to go, Eli. Real quick, as the tropics warms and humidifies, the subtropical jets are going to move northward. They're going to expand a little bit upward. Is that and that will create a northward conduit of forcings from the tropics, in addition to changes in the amplitude of the MJO. Have you looked at that interaction of the modification of the zonal mean state by climate, in addition to the forcing of the MJO?
That's a wonderful question. That's exactly what the motivation for this current effort that we have, because what we did so far is take a model and force it to have a stronger MJO. Let's think about Wacom, the more realistic model. We mess with the convection, we get a stronger MJO, we get this signal in the stratosphere. But as you said, in a global warming situation, everything changes, not just the MJO. What effect would that have? So to answer questions like that, we're trying to develop a realistic model, I mean, as realistic as these get, that well simulates the MJO and SSWs, and then that model we're going to put in an RCP 8.5 scenario to see whether this mechanism that we're proposing is robust or not. Right now, I don't have a question to your an answer to your question, but that's definitely something we're working hard right now.
Hey, thanks, Eli. Talk. I got to run. Bye.
We also have a question from Ross. Ross, you're unmuted too.
Hi, it's Ross Salowich again. Great talk. I'm going to begin with a very short comment and lead to a question. The comment is that, the big surprises we've had in the stratosphere recently are the incredibly cold, very stable conditions in the Arctic during its most recent winter, and then, of course, the sudden warming in the Antarctic. And further, we really care about the Antarctic vortex, not just because of the ozone hole, but the effect that circulation system has on southern hemisphere climate. So my question is, have you thought about how these mechanisms apply to the Antarctic polar vortex? Are we likely to see that becoming more disturbed as well over time, perhaps even leading to a super quicker than expected recovery of the ozone hole?
I mean, yeah, that's a great question. We thought about it, but we haven't done much work, so I can't tell you. Right now we're still at the phase where we want to make sure that this mechanism actually works to the Arctic by using this model that is realistic, hopefully in terms of simulating both of these things we're interested in. Once we have such a model, we'll definitely look at the southern hemisphere as well, obviously, right?
Thank you.
Thank you.
Any other questions? Oh, there we go. There's Tong Zhu.
Yeah, it's me again. So I'm a little interested about the last part of this, the whole evolution of SSW. So when the increase of polar vortex, then is there any more studies about how the warming happened, the temperature increase? Is there any linkage in your study or by other groups?
I think that's addressed here. So here, there's a few papers here that some GCMs predict more frequent southern stratospheric warmings in the future, and some papers saying that that's not necessarily the case. I think the bottom line of the present day literature is that we don't know whether southern stratospheric warmings will become more or less frequent in the future. The thing to remember is that none of the models we have right now simulates both the MJO and southern stratospheric warming. So if this mechanism I'm discussing is relevant, then the current models are not able to address it properly.
Okay, I see. Thank you.
Thank you.
Yeah, very interesting talk.
Any other questions? Also, if you don't have a mic or if you just don't want to speak, you can always chat your question and I can read it out loud. looks like that is it, Dr. Zieberman. I think, thank you for a great talk.
Yeah, thanks very much for all the questions. It was a pleasure.
Oh, we have another from Mike, last minute. You're unmuted, Mike.
No, I was just saying thank you in the chat.
Oh.
Really appreciate that. Please.
Thank you.
Okay, so I think let's ramp up. Thank you, Professor Zipperman, and I thank everyone for coming. We'll put the video on our YouTube channel, and you can find the thread on our seminar Google Sheet. And I look forward to seeing you in our next seminar. Thank you.